Hi, and welcome to Concept Based. We're doing a Year 11 extension concept today. This is permutations and combinations. And we're actually looking at the proof of one of the identities of a combination. Now, this identity gets proven in the classroom a couple of different ways. It gets proven using Pascal's triangle, which I'm not going to use. And then I'm going to prove it algebraically. But there's a second part to this. It says explain this combinatorially. So you have to understand why this is actually true. Now, as a maths student, shout out to Mr. Fardouli if he ever gets to see this video. He was my maths teacher for 6 years of high school. If you are a maths student like me, then the most common question that I would ask in Mr. Fardouli's class is why? Why is this the case? Why does it work? Now, sometimes proving something to me algebraically was enough. If I could do it algebraically and the algebra fell out and it was true, I could then accept that's true. But being able to explain this with language rather than algebra, I think really solidifies the concept of why this is true. Now, I do want to make a point by your reference sheet, as always, is that this formula is not there. So if we look at your reference sheet, you have this NCR formula, the combinations formula, the bottom one. So you can see I'm using the bracket for notation in my NCR on my working. Equation Editor doesn't want to switch it into NCR in the index form, so I'm just going to use the brackets, which is in your syllabus, and it can appear both ways in the HSC and has done so. So you do need to be using both notations. Okay, so we've got this part of the formula. We've got this algebraic substitution that we can make into NCR, being n factorial over r factorial outside of n minus r factorial. So that part we've got, but this part that it's actually being asked is not there. And it does state in your syllabus that, let me find the line exactly I'm looking at, show that, and then it gives this proof by selecting R objects from n distinct objects and so forth. So we do need to be able to prove it. Now, would they ask us to do a proof in the HSC? Probably not. But what they might ask us in the HSC, or what they might give us in the HSC, is they might give us information about the n-1 case, or they might give us, so they might give us some values that we can just substitute into, say, the right-hand side of the formula and the left-hand side of the formula. And then we might be asked to prove some other part in the middle, and that might result in us having to prove how many objects there are. So the ability to manipulate all of this information algebraically is necessary. It does state the proof in the syllabus, so they could ask it in the HSC. They just generally don't. But you never know what could pop up in the HSC. So let's go ahead and try and prove this algebraically. And then I'll try and give an explanation to you where you can be like, oh, of course, yes, that makes sense. That's the reason why this works in this way. So let's go ahead and do this algebraically. Now I'm going to have to write this a little bit vertically because the expansion of these is quite large and I want you to be able to read what I'm writing. So we'll see how we go. Now, when you are doing a proof, every single time you're doing a proof, the first thing you write is always the same. It is either LHS or RHS. Please don't restate what you are trying to prove and then do things to both sides of the equation and in the end prove that 1 equals 1. Like we don't want to do that. What we want to do is we want to get a right-hand side in the form of the left-hand side or the left-hand side in the form of the right-hand side. This one's pretty obviously easy which side we're going to attack because we can't really do anything to the left-hand side. My video is mirrored, so when I say left-hand side, I really mean the other side of the equation. Okay, so let's go ahead and attack the right-hand side. So we've got right-hand side equals. Now we can now use our formula. So we've got this formula that says that NCR is n factorial, but now we don't have NCR, we have n-1 CR-1. So it's not n factorial on the top, it's n-1 factorial on the top. And we don't have r, we have r-1. So on the bottom of the fraction, we have r-1 factorial. And then it's n minus r factorial. Now again, we don't have n, we have n minus 1 minus, so I'm now going to use another set of brackets, r-1 factorial. R-1 factorial. So it's pretty clunky, the first part of that we get out. And then we've got to get out the second part of the fraction. You can see why I have to work vertically just so that you can see what I'm writing on the screen. So the second fraction is n minus 1 factorial. Now we do have r. So we are over r factorial outside of n minus 1 again, minus, this time it's just r factorial. So I'm not going to, r, so I'm not going to use brackets. And I'm going to write it like this. Now, there's no big trick just yet. The big trick is coming. First of all, we're just going to tidy up the denominator of the brackets of the first fraction. So let's rewrite the first fraction as n minus 1 factorial. We can't tidy up r minus 1 factorial, so we're going to write that, r minus 1 factorial. But we can tidy up n minus 1 minus r minus 1 factorial. Because of the negative outside the front of the bracket, the signs are going to get shifted inside the bracket. So minus 1 minus minus 1 is going to disappear. It's going to be negative 1 plus 1. We're going to get 0. So we're just going to be left inside this bracket n minus r factorial. Now, the bottom one doesn't change, but I'm going to rewrite it just in a slightly different way so that I can explain this concept of where the trick is. So n minus 1 factorial over r factorial. And then I'm going to rewrite n minus 1 minus r factorial as n minus r minus 1 factorial. We're allowed to move that minus r minus 1 around as long as we keep the negative with the term, then that's fine. We can shift it. So we get it into this form where we have these two fractions that we're meant to be adding together. And here comes the trick. Now, do not do what might be, say, year 8 fractions, where you just cross multiply everything. If you do that, it's going to be chaotic. There's just going to be so much you're going to have to cancel down when it comes to the end that it can become confusing. What we want to do is we want to try and find as many common terms in the denominator as we can. And this is the trick. The trick is, as per my previous video, always make the big one smaller. Okay, so if we look at these terms in the base of the first fraction, we've got an r minus 1 factorial. And in the bottom fraction, we've got an r factorial. So which one is bigger, r minus 1 factorial or r factorial? Obviously, r factorial is bigger. It's one bigger. Well, one term bigger that we're going to be multiplying by. The other one, the n minus r factorial bracket on the bottom, is bigger than the second one because the second one is n minus r minus 1 factorial. So it's also one smaller in that case. So we're going to change everything to be the smaller one. It's easier to change the bigger one to the smaller one. Why is it easier to change the bigger one to the small one? Because remember, 5 factorial could be written as 5 lots of 4 factorial. We can always change the big one to look like the small one. So let's go ahead and change the big ones in both of them to look like the small ones in both of them. So here we go with our first fraction again, n minus 1 factorial over. Now r minus 1 factorial is already the small one, so we're leaving it, r minus 1 factorial. And then n minus r factorial is the big one because in the second fraction, it's n minus r minus 1. So we're going to change it to be n minus r lots of n minus r minus 1 factorial. Okay, that's the trick. Can you recognize that n minus r lots, 5 lots of n minus r minus 1, 4 lots factorial is the same. So you have to be able to recognize that. In the bottom fraction, so plus, we've still got the n minus 1 factorial. And now r factorial is the big one. So we're going to change that to r lots of r minus 1 factorial outside of n minus r minus 1 is the small one factorial. So now what we want to be able to see is that there are common things in the denominators of both of these fractions. We can see that we've got an r minus 1 factorial in both of them, and we've got an n minus r minus 1 factorial in the both of them. What we don't have in both of them is this n minus r term and this r term. So that's what we're going to be cross multiplying by to try and put our fractions together and simplify. So in the first fraction, we don't have r. So we're going to put r into our numerator of the first fraction. So we're going to have r outside of n minus 1 factorial over. And we do have all of the rest. So just for ease of writing, I'm just going to write all for the moment because there's a lot of terms in the base there. Now notice when I do times by the r, you know what? This is a full video. Let's do the whole thing. So we multiplied across by r. So now down the bottom, the terms we're going to have are r, because that's what we had to cross multiply by, r minus 1 factorial. And then the n minus r was already there, n minus r, and then n minus r minus 1 factorial. In the second fraction, plus, we have to cross multiply the n minus r across, right? That's the one that's not, come on. That's the term that's not in the other one, the n minus r. So we multiply across n minus r. Our top is still n minus 1 factorial on the second fraction. And so now down on the base of this one, we are going to have r outside of r minus 1 factorial. And we've multiplied by n minus r. So we're going to put in n minus r minus 1 factorial. And in the end, the denominators now look like the same, which is what we expected. Now have a look at those denominators. By making the small ones and then putting them together, cross multiplying, we've ended up with a special term down the bottom that we can actually put back together. So let's put that back together first. Here is r, lots of r minus 1 factorial, right? It's in both fractions. And here is n minus r times n minus r minus 1 factorial, which is in both fractions because we cross multiplied. Those are the expansions of the big ones. We made those by expanding the big ones. So now let's put them back together. So our first fraction is going to be r n minus 1 factorial. But down on the base here now, we're doing r lots of r minus 1, which is just r factorial. And we're doing n minus r lots of n minus r minus 1, which is just n minus r factorial. So the denominators become quite clean. And then the second fraction, we've got n minus r outside of n minus 1 factorial on the numerator. And in the denominator, we have the same, r factorial, n minus r factorial. Sweet. Okay, so now we definitely can put our fractions together. The denominators are the same. Let's go ahead and add the numerators. So we have r outside of n minus 1 factorial plus n minus r n minus 1 factorial over r factorial n minus r factorial. All right, so now in the numerator, we've got, well, in the denominator, first of all, we've got what we want because we're looking for NCR. And on the bottom of NCR is r factorial n minus r factorial. That's what the definition on the left-hand side is. So we just need to tidy up the top of this right-hand side. How do we tidy up the top when we've got these strange expressions? Well, you'll notice that the n minus 1 factorial is in both terms. So if we take n minus 1 factorial out as a factor, what would it be left with? Well, the first term, needs an r, and the second term needs an n minus r. So now we factorize that n minus 1 factorial. So now we get r factorial over n minus r factorial on the base still. And this term here has got r plus n minus r. So r plus minus r is going to cancel. And so we're just going to end up with n minus 1 factorial n over r factorial n minus r factorial. And we saw this before. That expression in the numerator is us taking the small version and expanding it out into the big version. So we actually have the big version there. N lots of n minus 1 factorial is n factorial over r factorial n minus r factorial, which equals the left-hand side. What a proof, right? So again, when we're going through this proof, what is the trick? The trick is splitting up the big one. In this one, this was the big one, we're going to split it up. In this one, this was the big one, we're going to split it up. Turning the big ones into the little ones gives you the ability to have that commonality between them, and you can go ahead and manipulate them. So what does this rule end up saying? It ends up saying that NCR equals n minus 1 CR minus 1 plus n minus 1 CR. What does this mean? Okay, now again, we're going back to the why, me as a student and maybe you as a student. You want to know why this is true so that it really solidifies into your understanding. So let's say we were picking a team from a group, and let's say this group was made up of the individuals A, B, C, D, E, F. And say we had to pick a team of 3, and we're saying, well, how many teams of 3 could we pick? There's ABC, ABD, ABE, and so on, and you get all of these large amounts of combinations. This picking a team of 3, I'm just going to indicate this way here, just an example, right? Picking a team of 3 here can result in 2 cases. It can result in a case where you either pick A in the team or you don't pick A in the team. So all of the combinations are either picking A in the team or not picking A in the team. So let's look at the first situation. The first situation is, let's say we do pick A in the team. If we do pick A in the team, then the number of combinations that we can make with A in the team is the people that are left. So the people that are left are B, C, D, E, and F. And we're picking 3 in our team, but we've already picked A. So we've only got 2 people left to pick. So we could pick a team of 2. So again, this first one was not NCR, there's 6C3. So in this second situation, where we're trying to say that this is equal to this plus the next one, we've picked A, but now we're only having to pick another 2 from 5, right? So this actually could be expressed as 5C2. There's one less object to pick in the team because A's already picked, but there's one less object to pick from because there's A's already in the team, so there's only 5 left to pick from. The second option, which we need to add to our combinations because A might not be in the first team, is if A is not in the team. If A is not in the team, then we need to pick the team from the remaining people. And if the remaining people, and the team we're picking is a team of 3. So we would have to pick 3 from these 5. Now have a look at these numbers. 6C3 equals 5C2 plus 5C3, which is the proof that NCR equals n minus 1 CR minus 1 plus n minus 1 CR. It's because of these 2 cases of picking a player and then getting the rest of the team, and not picking a player and picking the rest of the team. So hopefully that little proof there gives you this concept of like, oh, obviously that's why this has to work. Otherwise, if you're just after the algebra to be able to prove it, obviously that proof is up there. But the main thing that we want to look at is, can we apply this? In the HSC, could we be given information and then from that have to derive it? So for example, they might give us the number of combinations of picking a team when John was picked and a number of combinations when John wasn't picked. And then they just say, so what's the total number of combinations of picking a player? If you don't understand that that's related to that NCR, then you would never be able to step through that question. You'd be like, what do I do? And you start writing out lists of combinations. And as soon as you start doing that, it's not going to work because that's going to take up all of your HSC time. So scroll back through from the top, have a look through the proof, definitely practice it at least a couple of times and just make sure that you can do it. Making the big one like the little one and then factorizing out on top.